Today we will be talking about acid-base equilibrium. So I'm going to need you to get some paper out or your chemistry notebook if you still have it. And I need you to go ahead and title the page Acid-Base Equilibrium, with today's date being April 20th, 2016. The first thing we're going to be talking about is the equilibrium constant expression. So the main thing from this slide that you need to write down is the definition for the equilibrium constant expression, which is the first bullet point. It is the ratio of the concentrations of the reaction at equilibrium. For those of us who do not recall what at equilibrium is, these are for our weak There are weak acids and bases. This means we will not be dealing with strong bases when we're talking about our equilibrium expression constant. Okay, it's also important to note that the equilibrium constant is going to be represented by K. If you would like to write that down, you can. And the last thing that's important is that Ka is used for acids and Kb is used for bases. But you should be able to get that without writing it down. On this side, I need you to write down this equation. This is just a general chemical equation. Please note we do have these double arrows, which means it's at equilibrium. And I also need you to write down the KEQ equation. Here, if you're not aware, this represents a coefficient from the balanced equation. In the general equation, when I plug it into our equilibrium constant expression, which is what this one is, the big one, that same coefficient becomes the exponent if there is one. If there isn't one, we just leave it be. It's just an exponent of 1, which is just the same as whatever number it is. Also, you need to be aware that square brackets are how we calculate molarity, or they indicate that we have molarity. We're only going to be worried about molarity in the brackets. This KEQ equation is the products divided by the reactants. And another major thing you need to put is that pure liquids and pure solids will be left out of the expression. We will not put liquids and solids in our expressions, which means we have to be paying attention to our states of matter. I know lots of times y'all like to leave them off, but that's not going to be an option in this unit. There are 2 steps to writing the equilibrium constant expression. Step number 1, you should be writing this down, is to write the equation for the ionization of the weak acid or the weak base in water. The main thing here is water. On your homework paper that you picked up, if you don't know that you need to add water to it, you're not going to be able to write your expression properly. Also, water is H2O as a liquid. Some of you are still going to try to tell me it's a aqueous solution, which it is not. I cannot dissolve water in water. And then step 2 is to write the Ka expression. So you set Ka equals to the products, which in our situation from the equation above is H plus times A minus divided by HA. All we're doing is putting products over reactants in brackets. I want to do some practice with this. So the directions say for this specific equation that we need to write the expression for the acid dissociation constant. So we're going to write the Ka with the equilibrium expression. But before we do that, I want us to go through and identify in this specific equation, which you should be writing down now, what the acid, the base, the conjugate acid, and the conjugate base are. I hope by now you're okay with the acid loses its H to the base. The way I know that this is what happened is because when I come over here to the product side, hydronium happens to have one more H than water. Therefore, water was the base. And nitrous acid is the acid. And in the product side, hydronium is the conjugate acid, while nitrite is the conjugate base. I hope by now you're okay with writing those. This is not new. The conjugate acids, the conjugate bases, all of that, that's old. Okay, now let's go in and write our Ka expression. So Ka equals, it is always going to be products over reactants. So we're going to write our products first. So hydronium plus nitrite. Okay, those are our products. Notice they are in square brackets. They are not normal parentheses, square brackets. Okay, remember, before when we were discussing what an equilibrium expression was, there are no liquids or solids. Therefore, water does not get written in our equilibrium expression. So on the bottom, I just have H and O2. Later, we're going to go through and we're going to actually plug numbers into these and solve them. But that's not yet. It will be today, though. Let's practice another one. So again, this one says to write the acid dissociation constant. Write the expression for that. But before we do that, I still want us to go through and identify the acid or the base. So, in this situation, HClO2 is the acid. That is chlorous acid, not hydro. Hydro means it's binary. There are more than two elements, so it is not binary. Water is our base in this situation. Here, remember that H3O plus and H plus are used interchangeably. So yes, I am aware that we got rid of this H2O on the other side. However, this aqueous right here accounts for that in that it's dissolved in water. So this is the conjugate acid and this is the conjugate base. Okay, in our equilibrium constant expression, you need to set your equilibrium constant, which in this case is Ka, equal to the products over the reactants. So my first product is H plus, ClO2 minus, divided by HClO2. If we're having trouble, I should be back for tutoring tomorrow if you need me. Okay, we have one more example and then we're going to move on to some math. So in this example, notice it wants us to write the expression for the base dissociation constant. Remember, our base dissociation is Kb, not Ka. In this situation, if we're looking at what's going on in our reaction, one of these H's in water is being added to ammonia to make ammonia. So water is losing an H, which makes it an acid. Ammonia is gaining an H, which makes it a base. And over here I have a conjugate base and a conjugate acid. Remember, it is still products over reactants in these little square brackets, which mean concentration in molarity. I hope by this point you're starting to get the hang of it. Products over reactants, products over reactants, products over reactants. Okay, once we are done with this step, I need you to skip 7 lines on your paper. I need you to count out 7 lines. Once you have counted out your 7 lines, I need you to write calculating equilibrium at the at the top of your heading after your 7th line, it's blank. Using ICE tables. Using ICE tables. So we're going to calculate equilibrium using ICE tables. I am aware that you do not know what an ICE table is, but we are about to go through this. As we are going through these, we are going to go in and fill in our blank 7 lines as we're going. Okay, so step 1 is to write a balanced equation. Write a balanced equation including states of matter. So we're going to write a chemical equation. If it's either the words and we're converting it to a chemical equation, or maybe they already gave us a chemical equation. And then, once you are done writing that step that I underlined, we are going to come over here, and I am going to find my eraser first. Okay, my eraser won't. Okay. That's not going to work apparently. But our specific equation here is AA aqueous yields BB aqueous plus CC. Okay, that is the exact same equation that's over here on number 1. So I'm going to move it back. If you don't have it, write it down. It's okay. Okay, step 2 says, draw an ICE table. And then under draw an ICE table, I want you to write these 3 bullet points under it. That the I stands for initial concentration. That is the amount that we start with. And that is generally given to us in the equation or in the problem. The C represents change in concentration, so how much of it is changing. And then E represents equilibrium, that's like our final amount. So I is initial, C is change, and E is equilibrium. I'm going to move back over here. And I'm going to go ahead and do step 2, which is to write I, C, and E over on the side, the left-hand side. Those should be on 1 line each. We're not skipping lines in between because we're going to have to do some calculations in a little bit. So we should have used, at this point, 4 of your 7 lines that you set aside. As we go to this slide, I'm going to have to rewrite what you had already written at the top. So here I have AA aqueous yields BB aqueous plus C aqueous. And you should have written ICE. So, this gets us to step number 3. Step number 3 says, insert the values for initial concentration. That's it. We are going to put in the numbers that the problem gives me. At this point, I am going to make up a random number. And I am going to say that the problem gave me 1.5 molar concentration of A. Now I want y'all to understand, this reaction, the initial part, is before any reaction actually occurs. Which means that my products, I haven't made any of them. So they're going to have 0 here. Both of them. We haven't made any products. All we have is this reactant that gave us. Step 4 says to let X be the common factor, the common factor in the concentration change. Let X be the common factor in the concentration change. So I'm about to have to rewrite everything again. That's okay, we're still on our 4 lines out of the 7. We haven't done anything else yet. So X is going to go in the change part, so the C column, not column, row. So I have AA, B. I understand that I did not write the states of matter at this point, but they should already be on yours. Okay, so this is what your paper should look like up to now. How this goes is that I'm going to subtract X from the one that already has it, like a number. And I'm going to add them to the other side of my reaction. Because I can't take something away if there's nothing there. Step 5, as we're going through this, is to add up our initial concentration and our change concentration and write it in equilibrium. So we're going to add up I and C, and then we're going to write it in E. So in this situation for AA, I have 1.5 minus X. I have X and I have X. Please make sure that your ICE table looks just like mine does, except yours should have states of matter. So all I did was add up the columns, just like we do in math, to get these numbers. 6 is a specific situation. Step 6 is a specific situation. This says to insert the value of the equilibrium concentration if given. Insert value of equilibrium concentration if given. This part is the most important part. Most of the time you will not be given this equilibrium concentration. But if we look at this number down here at the bottom, or this little picture, I can zoom in some. I know it's still hard to tell, but notice our ICE table has X's in it. This one has a specific number down here in the equilibrium. That means that it had to have told me this number. Okay, our product still started at 0 because product started at 0. But I had to add some X to get 0.48. We are almost done with these steps. There's only 8. Step 7 is to actually plug in your equilibrium numbers from your ICE table into the Ka expression. Plug in your equilibrium numbers into your Ka expression. So the generic Ka expression in this situation would be products over reactants Okay, so in this specific situation, I have X and I have X, that's a time sign. I'm going to divide it by 1.5 minus X. All I did here was plug in our equilibrium numbers into our equilibrium expression. What you need to know at this point is this minus x, we are never going to worry about it because it's such a small number we don't really care. So this is going to go to x squared, and then we're going to divide it by 1.5. That's it. We are going to need to set this equal to something. And so at this point, I'm just going to choose an arbitrary number, and I'm going to say it's 2 times 10 to the negative 5. Okay, every specific weak acid has a Ka value. This is just a generic number that I chose out of the air. Okay, step 8 is the next part. Step 8 is to solve for x. So you need to write 8, solve for x, just like we would in math class. So in order to get x by itself, or x squared by itself, I need to multiply those two numbers together. And they come out to 3.0 times 10 to the negative 5. We should all be with me up until this point. All we are doing is basic math. Sorry, it turned. Okay, once I have solved for x squared, then I need to square root it to get just x by itself. So I am going to square root both sides so I get x equals. I hope y'all have a calculator because you should be doing this while I'm doing it. And I get 5.48 times 10 to the negative 3. Remember, everything that's in brackets is in concentration of molarity. Also, you would need to tell me that X is the B concentration and the C concentration. Because I don't know what those are at this point, but I need to identify that those concentrations are the same, and they're both equal to this 5.8 or 48 times 10 to the negative 3. Once I have this value, you should be able to put it into, like, it'll either be H or OH that we're solved for, and you should be able to take that number and put it into the pH or the POH equation. The last thing we're going to be talking about is percent ionization, because that's in your other packet as well. It's just like every other percent that we've done. It's part over whole times 100. But in this situation specifically, it's the equilibrium part divided by the initial whole. So you should see here that these are different. At the bottom is the initial number that it gives me in the problem, in the words. And at the top up here is our concentration of either hydrogen, if we have an acid, or hydroxide if we have a base. And every single time we do times 100, because it's a percent. So if we go back to our numbers from before, I had 5.48 was my equilibrium concentration times 10 to the negative 3. And I'm going to divide it by that 1.5. You should be writing these in those extra lines that you still have left under those 7 lines we left blank. We are going to times it by 100. What percent ionization does is it tells us how much specifically of the acid ionized into its ion, so broke up into its pieces. And when I put this into my calculator, I get 0.365%. That is not very much ionizing. Remember, our strong acids and our strong bases, they break up 100%. This acid was so weak that it only broke up 0.365%. So this is why we have to do these equilibrium tables with acids and bases that are weak, because not very much of it is breaking up. This is also why I can just get rid of that minus X in our ICE table, Because it's so incredibly small, it doesn't even matter.